Alright, so in this lecture, I'm going to talk about hierarchical modeling. This was the lecture for day 4. I couldn't record it because the network was crashing all the time. So I'm recording it offline so that you can go through the slides with me once. Alright, so the issue that we're going to study in this lecture is a very simple experiment. So we are going to look at a self-paced reading study that is quite a well-known study in psycholinguistics. It's by Grodin and Gibson. It's their experiment 1. And this study actually compares object and subject relatives reading times. Okay, so the scientific question is the following. If you have a subject relative, like this sentence 1b, what's special about this sentence is that there's a main clause. The reporter was hoping for a good story. And inside the main clause, this subject noun phrase of the main clause is modified by a relative clause. And what's special about that relative clause is that there's a verb inside that relative clause that takes as subject the subject noun from the main phrase, that is reporter. So this is why it's called a subject gap, because the relative clause verb has a gap supposedly just before the verb that connects to the subject here. So that's why it's called a subject gap. And by contrast, there's also this object gap construction, which has the same setup as a subject gap. The setup is that there is the main clause, the reporter was hoping for a good story. And then again, there's a relative clause here. But this time, the verb inside the relative clause takes reporter, the main clause subject, as an object of that sentence. So the subject of sentence is reporter and the object is, the subject of sentence is photographer and the object is reporter. And so because objects typically occupy a gap position here, at least in linguistic theory, right after the verb, so this is called an object gap. So these two conditions are called object and subject gap conditions, right? You could also call them object and subject relative clauses. And so the theory is that, in theoretical prediction rather, is that if you record the reading times at the verb sent in the object and subject relative, you should see longer reading times in the object relative, because the distance, the linear distance between the subject here, reporter, subject of the main clause that is, and the verb sent is longer in the object gap condition than in the subject gap condition. That's the idea. Okay, so we are comparing reading times at sent in object and subject relatives. So what I want to point out here is that actually this design is very heavily confounded. So I wouldn't take this design overly seriously. And the reason for that, there's a message here. I don't know what this message is. Sorry about this. Oh, I see. It's just transparency. Okay. So, so the design is confounded because what's wrong here is that the pre-critical region in the object and subject gap is different. In the object gap, it's photographer, and in the subject gap, it's who. So one thing that we know about reading processes is that there's a certain amount of spillover from the preceding word onto the current word. Right? And if the pre-critical region is non-identical in two conditions, then I would consider the design confounded. So today, 20 years ago, I would have run such a study happily, and I have run such studies myself. Not in English, but I have done similarly confounded studies. But today, I would be very wary of trying to interpret reading time differences into sentences that do not constitute a minimal pair. Okay, so this is very important. Right, we often forget that the real, issues behind an experiment design appear at this stage, at the planning stage, right? So the actual running of the experiment and recording the data and so on, this is a very secondary issue. I mean, even at the first stage, you can run into big troubles just setting up the design. So this is an example of why I would not want to run such a study. But nevertheless, I mean, the data exist, and pretty much everybody in the field has run such confounded studies. So it is what it is. So we're going to try to analyze it, right? Knowing that, I wouldn't take the results too seriously when when the design is confounded in this way. So anyway, so we load the library as usual, load the data which is available in the library, and I want you to pay attention again to the design aspects of this experiment. So what's nice about this data set is that it's a clean Latin square design that actually worked, so it's important to see that they set it up correctly. And it has this characteristic cross subjects and items design that you guys might be familiar with from linear mixed modeling, right? So let's just quickly spend a few minutes trying to make sure that the data actually conform to these expectations. So this was the plan to run a Latin square design with cross subjects and items, and we want to always check that these assumptions are met. Okay, so as I have repeatedly said in the course, it often happens that people just load their data set and just run the analysis. You should never do that. First, spend a few minutes just checking whether the experiment assumptions that you have set up are met. Okay, that's a very important step. It takes 5 minutes. It's worth doing, right? So first, let's check that this is actually a Latin square design, right? So first of all, I want to check how many subjects I have. So that's my old style coding. Shows 42 subjects, 16 items. So 42 times 16 would be 672, right? That already tells me that each subject is seeing each item exactly once. That is your classic Latin square design, right? And so I can also use this nice xtabs function to check how many instances of each condition was seen by each subject. Okay, so this is what the command is. I'm showing you the first 4 lines, and what you see is that each subject is seeing 8 instances of the object gap, 8 instances of the subject gap. That's as expected, right? Because there are 16 items. It's a balanced design. 42 subjects, each subject seeing 8 instances of each of the 2 conditions. Okay, so everything seems to be working out. By the way, in real life, I would not just look at the head, the first 4 lines of this output. I would look at the entire output, but I just don't want to print it out here. That's the only reason I'm showing you the first 4 lines. Okay, in real life you would look at it. So look at all the output. So what is a Latin square design? I'm sure all of you know this, but I just want to make sure that we are all on the same page. So if there are 2 conditions, the way you set it up is that the way the Latin square design is set up is that you have 16 items, 16 unique items, each of which has an object gap condition and a subject gap condition. So you remember what I'm calling an item here. If you go back to the example I showed you, these 2 sentences constitute one item. The item ID is 1 here. Why? Because there are 2 instances, 2 conditions here, but they all have the same words. They're just rearranged to form an object or subject gap. That's the big idea here, right? So that's what I'm calling an item. So each of these items actually has 2 versions of the 2, conditions. And so the Latin square setup is that I will create those 16 items, each with 2 versions. Then I will alternate the object and subject gap in one list and put the opposite alternation in the second list. So which I'm calling group here. Okay, you can call it a list or a group or whatever, right? And so the idea with the Latin square is that each subject that comes into the lab is assigned group 1 or group 2. Okay, so they end up seeing 16 instances of each item. This is the characteristic of a Latin square design. So if there were 4 conditions, you would have 4 groups. If you had 8 conditions, you would have 8 groups. If you had 16 conditions, you would have 16 groups. If you had 32 conditions, God forbid, you would have 32 groups, right? So that would be the setup. So what we are going to do is that when we set up the experiment, it's very important to make sure that you get random assignment of each subject to each of the groups. So I'm calling them, unfortunately, I'll name this order. I should have called it group. What I'm trying to do here is I'm setting up an ordering, of group 1, group 2, 11 times, so that anytime a subject comes into the lab, I will just give the first subject group 2, second subject group 2, third subject group 1, and so on, right? And it goes on like this. So this randomized ordering ensures that at the end of the experiment, I will have equal number of group 1 and group 2 conditions. And importantly, I'll have randomly assigned these guys to group 1 and group 2. So it's very important to make sure that you do this random assignment, because if you introduce some systematicity in the way you assign each subject to each group, you will introduce bias in your experiment, right? So a common example that I use is that, for example, at the beginning of the semester, when all the students are fresh and excited about their studies and so on, you assign all the incoming subjects to group 1, let's say, right? And then by the time the semester ends, when everybody's exhausted and unhappy and tired, you start assigning them to group 2. This is of course an artificial and extreme example, but what you have done is that you have now introduced potential bias into your design, because there could be a systematic group effect now, right? That could actually change your results in unexpected ways, right? So that's the setup of the Latin square design. And so one important property of the Latin square design, the Latin square design is very popular in psychology and linguistics. And the reason for that is that it actually meets some optimality conditions for estimating the parameters. Right? I can't go into that in detail. That's a whole field in statistics. It's called optimal experiment design. So if you study, the literature on optimal experiment design, you can just Google it. You'll find some textbooks. It's a deep area, how to design an experiment such that you get the most efficient and accurate estimates, etc. So the Latin square format is very well designed for getting optimal, properties of an experiment. And so, but intuitively it should be clear, that what I'm doing is I'm trying to avoid showing item 1 in both its realizations to each subject. Each subject is going to see only one of the two items, one of the two instances in an item. And the reason I want to do that is I don't want to expose the same subject to the same words in the same experiment, right? So if the subject sees the object gap and sometime later in the experiment they see the subject gap, they are now familiar with that sentence. So their expectations are going to change and their behavior will change. So I don't want to do that. I will only show one instance of these two conditions to the subject for that reason. This is really important. I know that in ERP research, often people show all instances of all items, but that's a topic for another day. It's not important for us. What's important for us is that we want to implement a Latin square design, and this English relative clause study actually implements that correctly, right? This is good. Okay, so one thing I want to quickly show you before I go any further with the analysis is that I want you to appreciate how you could generate, fake data that has the properties that this design is set up to have, right? So you load the mass library, and what you can do is you can decide on the number of items, the number of subjects. And what I'm literally doing now is I'm setting up the Latin square. I've got 16 items for group 1, 16 for group 2. In group 1, I've got object and subject alternating. And in group 2, I have subject and object alternating. You should run this code yourself and you'll see what's coming out of it. Okay, I won't do that for you. And then what I do is I assemble the group 1 data frame, right? So I'm assuming that I'm exposing 42 divided by 2 subjects. That means 21 subjects are being assigned to group 1 and 21 subjects are being assigned to group 2. So what I've done is I've replicated the column, the Latin square column, this one here. I've repeated this 21 times for group 1 and 21 times for group 2. That's what I did here, right? That's what I've done here. And then I just row binded them. So I just pasted them together, one on top of the other. So I've got group 1, group 2, order doesn't matter here, right? As you read in the textbook, there is this concept of exchangeability that is very important in repeated measures designs. And that's the reason why I can put it in whatever order I like, it doesn't really matter. Okay, so I've put together this fake data frame, and notice that it has the right number of columns. So that's a big relief, right? I got it right. And then what I do is, or what I can do is I can add a subject column. So I'm going to repeat for the 42 subjects, n sub is 42. Each time I'm going to repeat it 16 times, right? That's because that's what I did with the fake data frame here. And then I added I've reordered the columns here, and then I added a predictor column, which is sum coded conditions, object gap +1, subject gap -1. This is that sum coding stuff that I mentioned throughout the course, right? So this is what the final data frame looks like. Notice that what's missing in this data frame is the actual data, right? There is no data here. We're going to, although I will not discuss this now, but what we are going to do, where I'm going with this, right, in the long run, I guess, is that I'm going to go row by row and produce some simulated data here by looking up which subject, which item, which condition I'm talking about. These are the 3 pieces of information that I need, you know, to produce a simulated data point. Now, I haven't discussed this. I will not discuss how to produce this fake data column here. However, I have discussed it in great detail elsewhere, right? So let's take a look. Where is it? Oh yeah, let's go to my homepage. So what I want to show you is that I actually have another draft of another textbook, which is the frequentist data analysis book. If you look under my publications, there's all the upcoming books that we have in progress at the moment, and there's this one here, number 4. So Vasisht, Chad, Burki, and Reinhold Kliegel. So this is called Linear Mixed Models for Linguistics and Psychology, the comprehensive introduction. And in this book, what I've done is I've got a chapter on simulating data, right? On simulation, using simulation to understand your model. So what I do in this chapter, chapter 8, is that I'm going to show you in this chapter how to generate simulated data in once you created a data frame like this. Okay, so this is extremely important, this skill. Of course, I cannot discuss this in today's class, and the reason for that is that it's simply there's simply not enough time, right? In 5 days, there's only so much we can do, but you should spend some time studying this chapter. It's an extremely important chapter in this whole discussion about simulating data. Okay, this will become our bread and butter activity. When we design a new experiment, we still start by simulating some data to understand the properties, of our design. So notice that my simulated, this is the real data again. So one thing to notice is that this is the fully crossed design. That's what that means is that each subject is seeing each item, right? Each subject is seeing each of the 16 items once. Okay, so that's a cross design. It's crossed because subjects are crossed with items here, right? Of course, I could have shown them more than once, right? Each subject could see more than one instance of each item, but that's something that you will see in ERP research, but we don't do that in my lab. We always implement this kind of unique exposure, to each item, even in ERP research. Okay, so the interesting thing now, the reason I was harping on and on about fake data simulation is that really what we want to do is we want to use the subject, item, and relative clause condition, which condition it is. These 3 pieces of information we want to use to generate simulated data, and the way we're going to do it is by defining a particular statistical model, and that statistical model actually implies a generative process. So I want you to always think about data as being a random variable, which is what it is, right? And to always think about what the underlying generative process is that you're defining when you're defining a model. Okay, so in the simplest case, if you're fitting a simple linear model, your underlying generative process would assume a normal likelihood with some mean and some standard deviation, and the mean is determined by the subject object relative clause coding for each row in your in your data frame. So I would just decide whether the row 1 has +1 or -1, and then I can compute this if I know alpha and beta, or if I have an estimate, right? And that allows me to generate simulated data, you see. So this is what we are actually assuming that the actual data has been generated is a random instance, you know, of this likelihood function. Okay, so here we go. I've just redone the contrast coding just to remind you what it is. And as I said many times before, the normal likelihood doesn't seem super well motivated, so we would actually use a log normal likelihood, right? All this has been discussed, so let's switch to the log normal now. Remember that the alpha, beta, and sigma are now on the log scale. What is being produced from this likelihood, or from this PDF, is reading time in milliseconds in this case, right? So one interesting thing to notice in the data is that if I plot the mean reading time of each subject, right? It's easy to compute because I have 42 subjects. I can look at all the data points for each subject for the critical conditions. The fillers are not available to me. Okay, so I don't know what the reading times in the fillers were, but if those data were available, then I would certainly include those in my calculation for the mean reading time. But we have what we have. We have the subject object relative clause data, just 16 data points from each subject. Yeah, so each of those 16 data points for those 42 subjects can be used to compute the average, you know, reading time for each subject. And you notice that there's a lot of variation between the 42 subjects. There's a couple of subjects that are super slow, and a large number are relatively fast, and some are extremely fast. So I guess these are MIT undergraduates. Okay, so these people tend to read, on average, they tend to read pretty fast compared to, for example, North Carolina or some other university in the United States. And one thing you'll notice is that, you know, if you expose German undergraduates to sentences in German, they tend to have an average reading time that is much larger than English for some reason. I don't know what the reason is. The same thing happens with Japanese and Hindi and Persian, Armenian, and many other languages that I have studied, or my students have studied. And the English speakers tend to read a little bit faster than many of the speakers that we encounter in other languages. Mysterious reason, I don't know why. Probably has to do something with the script, maybe. Okay, so what's interesting now is that we can elaborate on that simple linear model, and the way we will elaborate on it is that we are going to add by subject variability in the mean reading time, which we already see in the data, right? This variability needs to be accounted for, and the way we are going to do it is we're going to elaborate the simple linear model such that we have an adjustment to the intercept for each subject. So let me now switch to my Blackboard, right? So what I want to say is that we are assuming that graphically, you know, what we are assuming is that overall there will be an effect of object and subject relatives, right? So subject relatives, object relatives. If I look at the mean reading times here and the mean reading times here, I should see an increase in reading times, right? Between object and relatives on average. So this is the average over all the 42 subjects. This is a simple linear model, right? Oh no, I wish this thing would not behave like this. And so what I wanted was this. So this is the simple linear model. Y is equal to alpha plus beta times S. Oh, so what this model is saying is that when SR is coded as -1, you get this average reading time. So this is the reading time here, right? When you have an object relative that is coded, sorry, this is -1, right? And the object relative is coded as +1, then the model predicts that the average reading time will be this, right? So the difference in reading time, this difference is the difference in relative clause processing time. So that's the average difference, right, that we're talking about. So that's your simple linear model, right? And what I want to say is that we are observing that some subjects are actually slower than average and some subjects are faster than average. So there's variation, you know, in the intercept across subjects, right? So we're going to characterize that intercept mathematically by assuming that we not only have an average slope, which is that thick white line I showed you, this guy here, right? We also have an adjustment by subject, which I'm going to call UI. Each subject has a separate, a numerical value, which I'm calling U1, that adjusts the intercept up and down, up or down, right? So if a subject is slower than average, then that U sub 1 for that subject would be a positive value. If that subject is faster than average, the average is alpha here, right? Then that U sub 1 for that subject will be negative. If the subject is exactly, it has the same mean reading time as the average of those 42 subjects, then U sub 1 will be 0. Okay, so this thing can be positive, negative, or 0. This thing here, right? That's my intercept adjustment. Everything else remains the same. Beta times SO plus epsilon, right? So the epsilon is my variance component. Sorry, this is terrible handwriting. Epsilon is the variance component with mean 0, normal distribution with sigma as the standard deviation, right? So that's how we've learned how to write the model. So of course I could have written this model like this, right? Don't be confused now. I could have written y is generated from a normal distribution with mean alpha plus u sub 1 plus beta times SO and sigma. It's exactly the same statement, these two things, okay? All right, so one interesting thing is that I need to have a separate ID for each intercept adjustment for each subject, the u sub 1. And the way I'll do that is that when I have my data frame, I've got like subject, item, SO. Remember my fake data, 1, 2, 3, 4, etc. Is my subject ID, and then I have my item ID, let's say 1, 1, 1, 1, and so on, right? The data continue like this. And I've got, let's say, plus 1 or minus 1 or whatever, right? So, hey. So the idea is that I'm gonna take a walk through each of these rows in the data frame. There are 672 rows, right? 672 rows, right? So for each of those rows, I'm going to look up for the first row, right? For the first row here, I would look up what's the subject ID, right? The way I will ask that question, in mathematical notation, is that I will write U, how do I do this? Yeah, U subscript subj in the nth position, nth row of the data frame, right? And can be anything from 1 to 672. What is the subject ID in the nth row of the data frame? So that's this syntax for the variable U sub 1, right? So this 1 refers to the U sub 1, this intercept adjustment, and I'm figuring out which subject I'm talking about, which adjustment are we talking about, which subject's adjustment are we talking about. And I'm doing that by writing this statement, and what this state, you should read it like this, that looking up the nth row of the data frame and figuring out what the subject ID is. So if n were 2, then the subject ID in row 2 would be ID 2. In the first row it would be 1, and so on, right? So this way you can look up the subject ID from the data frame that you have. Of course, now you have to be careful. Always check your data frame, right? You have to make sure that the subject IDs are correct. This is not always the case. We sometimes make mistakes, okay, in the way we set up the subject IDs, to make sure that the subject IDs actually represent the data from the particular subject you're talking about. These are just sanity checks that you should do to make sure that the data frame actually satisfies the assumptions that you're making in this kind of statement. All right, so the upshot of all this is that we've added a varying intercept here for each subject, and now we have two sources of variance, because now we not only have sigma here, this is actually the average within subject variability, okay, but we also have between subject variability represented by this intercept adjustment, which has some standard deviation sigma u1, okay. So there's two sources of variance now in this model. This is what adds noise, in the data. This is what makes it very hard to actually get accurate estimates for your the effects of interest, whatever you're looking for. So another thing to notice in the data is that the items also vary. So some items are very fast, are read very fast. Some items are read relatively slowly, right? So this can happen because you've got verbs of different length, right? So this is slide 19. So if we go back to the earlier slide, if you remember, here we have a short word like sent, but you could have another word like investigated, okay? So that would take longer to read. So that is why you end up with variability by items, okay? By the way, I want to point out that some people do something really insane. I consider that insane. When they're analyzing the data, they will compute the residuals, over the items, and then analyze those residuals as a dependent variable. That doesn't make any sense. I mean, if you got a planned experiment and each of your items has the same verb each time, but there is some between item variability, this random component can be captured in the model, right? You don't need to residualize the data. So I never understood why people do this. Sometimes when you have a badly confounded design, then you do need to residualize, right? But then the question I would ask is, why did you set up your experiment in such a messy way, right? You should spend some time designing a good experiment instead of designing a bad experiment with confounded items, So for example, the worst kind of thing I have seen in my life, and this is appearing in journals like Cognition even today, the worst kind of experiment that I have seen is that this word in the same pair of items, this word is sent and this word is investigated. And so people are comparing reading times for sent versus investigated. I mean, come on, like that is pure insanity, right? So there are papers like this out there. If I get a few minutes, I will show you one such paper, okay, that appeared in Cognition. So just to show you that I'm not making this up, people actually do this kind of stuff, So, but you should never do that. I mean, if you're in a situation where you have to residualize your dependent variable, the patient is already dead. Just forget about it and start over, okay? So anyway, we were back here. I was talking about by item variability. So, just as we talked about the fact that, we had some average reading time for subject and object relatives, and each subject had a different intercept, so those were the green lines that I drawn. I could also represent the fact that different items have different intercepts. Some are slower than average, some are faster than average, right? So that's what we've done here. We are adding, just like for subjects, we're adding another term here, which is an adjustment for each item now. So I'm going to walk through the data frame. In the nth row, I'm going to look up which item ID I happen to have, and then I'm going to plug in an adjustment to this to the intercept alpha for each item as well. So basically what's happening now is that the average intercept alpha is getting two adjustments simultaneously, two independent adjustments, okay? One is by subject and one by items, and the item adjustment is assumed to come from a normal distribution with mean 0 and some standard deviation sigma W1, right? So now we have three sources of variance. This is the mistake here, right? I want you to look here. This is actually a typo. It should be sigma U1, because what I've written here is that each subject has a separate standard deviation. That is stupid. Let me just fix that. This is not what I wanted to say here. I'm gonna push this and change this, so it should be called U1, right? So it's very hard to get everything exactly right, in this kind of stuff. So anyway, so what should happen once I compile this file is that this should change to sigma U1, right? So the model that we now have is a varying intercepts model with crossed varying intercepts for subjects and for items, right? So what we are saying is that there will be an adjustment to the average alpha here. This alpha, which represents, sorry, this is not alpha. what am I talking about here? The alpha is this midpoint here, is the average reading time, right? So this the alpha is going to be adjusted up or down for each subject and for each item. So I can look up subject 1, item 4, for example, and I would have an adjustment. Okay, or if I want to just look at the subject adjustments, I will ignore this term, right? Sorry, I'll ignore this term, and I'm gonna simply add to the alpha this intercept adjustment by subject to get that subject's intercept adjustments. Remember that U and W are independent of each other. They're independent. Why do I know that? Because I've defined two independent generative processes here. If I define some kind of relationship between U and W, then they will not be independent. But we never design those kinds of experiments in a crossed by subjects and items design. Okay. So anyway, so these two terms, you know, the U and the W term, are representing between subject and between item variability, right, in mean reading time. So they're capturing an important property of the data, namely this between item variability and what we saw earlier, the between subject variability, right? So this is more realistic for this kind of design. But one thing to notice is that we have added one more variance component in the story, right? So this is going to affect our uncertainty of the estimate again. So this is both good news and bad news. Okay, it's good news because it's more realistic. It's taking into account that both subjects and items will vary, right? But it's bad news because it's gonna increase the uncertainty of our posterior. Okay, so this should have corrected. Does not the preview function. This preview. Software doesn't automatically update my file. So let me just quickly reload this file. Somewhere here. Right, so you notice that this file has just been updated, right? So it should now show the correct thing. Right, so if you look here, there it is, right? I fixed it now. What's going on? Just like these Macs, like they've over-engineered the hell out of these things. Anyway, so what I have now, I've fixed this now. You see that? It's sigma U1, this sigma W1. This is correct now. So there are three sources of variance, and what I'm showing you here, side by side, is the between subject variability. So I just estimated the mean, you know, reading time for subjects and the mean reading time for items here. And what you should notice is that there's a lot more variability in the subjects than in the items. This is as it should be, because we designed, or rather Grodner and Gibson designed the experiment very carefully, right? So they had items that were minimal pairs, or as much as is possible given the confounded design. And so between the items, there's not that much variability in, you know, average reading time, but between subjects, there's a lot more. Right? This is usually the case. Subjects vary a lot. They bring the most variability, sources of variance into the model, you know. So subjects cause the biggest source of variance because there's a lot of individual difference. There are a lot of individual differences between subjects, right? Of course, you could set up your experiment such that item variability is also very large, right? You could set it up. And there's actually a paper by Tal Yargoni, right? So let's go here. This is worth digressing and discussing for a few seconds. So there's a very important paper by Tal Yargoni, generalizability. It's about generalizability. So his basic complaint, you know, is that in a lot of research, what people do is that they don't allow enough variability in the items, and if you don't allow that much variability in the items, you can't really generalize over them, right? So what we do, the whole point of the random effects model or this linear mix model is that you're taking a sample of subjects, right, and you want to use that sample to generalize to the population, right? That generalizability is an important property that we want to aim for, in our experiments. So for example, you can't just take one subject's data and then make a statement about the entire population of speakers of that native language. You would need a sample of subjects, right? So the same thing happens with items, right? You want to make sure that you've got a broad range of items. Obviously, these are not random samples, but still you want to be able to generalize over them, and that's why you need to actually allow more variability, right? This is really this is a very strange thing on the surface, because what he's saying, what Yarkoni is saying in this paper, amounts to actually increasing the amount of variability in the data. That means the standard error of the fixed effect is gonna actually get bigger, right? But for Yarkoni, that's okay, because he's not trying to do null hypothesis significance testing. He wants more realistic data, right? So it's important to understand that people get confused about this, because they always think about null hypothesis significance testing. Is the effect significant or not? That's not even the point. We are trying to model reality here. We want to take the variability seriously, when we are trying to understand reality. And so between subject variability and between item variability will be taken into account. And so the way we did that was by adjusting the intercepts, right? But we can go even further. We can also adjust the slope. So the slope, right, if you remember in this simple linear model, right? So in this simple linear model, the slope is actually telling you, right, if I've got SR here and OR here, and I've got like the averages of these two guys here, I fit this model like this. This slope is actually telling me the difference between the object and subject relative, right? So, but this slope might also vary by subject, right? So some subjects might have more extreme slope, and some subjects might actually have flat slope, right? Or even negative slope. There might be subjects who actually find object relatives easier than subject relatives. I mean, let me rephrase that. I'm not saying that they actually find them easier, but rather what we observe in the data is that object relatives are read faster than subject relatives for some subjects. This could be accidental, okay? We don't know if that's actually true. This is just data, right? So basically what we want to do is we want to take this average slope beta and we want to adjust it by subjects and by items, right? So I can now quickly go, oh, there's another typo here. This should have been 2. I'm so sorry. That's what happens when you're writing everything really fast. So what I wanted to do here is, what I want to write is that the slope for items is going to have subscript 2 always, right? This should have been 2. I've just done that and I'll fix it in a moment. So what happens as a consequence is that now we have 4 variance components for the random effects. For subjects, we have intercept and slope adjustments, which are independent, by the way, here, right? And for items, we have intercept and slope adjustments, which are also independent. How do I know that they're independent? Well, I can just eyeball this mathematical statement. It says I've got separate random variable specifications for each of the variance components, right? For each of the sources of variability. And because I'm defining no correlation between U1 and U2, by definition, there isn't any here, right? So I could have actually, this is very important, okay? So this statement here about the intercepts and slopes is basically saying, the following, right? So I'm literally saying that U1 and U2 are coming from a bivariate distribution. So this should surprise you, right? Because they're 2 independent distributions. But what I'm saying is that the variance for U1 is sigma U1 squared, and the variance for U2 is sigma U2 squared, but the covariance is 0. This is literally the same. This is the same statement as defining independent generative processes for the 2 variance components, sigma U1, sigma U2. These 2 statements are equivalent, right? So you shouldn't get confused about this, right? Okay, so I'm assuming 2 independent random variables here for subjects and also for items, right? So this is my model now, and I have 5 sources of variance now. Sigma sigma u1, sigma u2, sigma w1 and w2, right? So this is now giving me what we call, this model is now what we call the varying intercepts and varying slopes model with no correlation between the intercepts and slopes. And now, of course, you know where I'm going with this. I'm going to go and fit the so-called maximal model, the notorious maximal model, right? And this maximal model will have the following elaboration, which you've seen before. We're going to have the, for the subjects u1 and u2, we're going to have a variance covariance matrix defined, and for items also we'll have a variance covariance matrix defined. And what that means is that we've added one more parameter here, the rho u and the rho w, okay? And as I'll show you later, there will be a prior defined on sigma, which will be a normal 0, 1 prior. This is the log normal likelihood, of course, right? Because sigma is now on the log scale. All right, so what's going on here? This is the Bartol maximal model, right? And this model is relatively straightforward to implement in in BRMS and STAN. We're going to define some vague prior on alpha. This is not a very realistic prior, but we can live with it for now. And for alpha, for beta also, we'll define a pretty vague prior. Okay, on the log scale, a 0, 1 prior is very liberal. It's allowing a lot of variation. Okay. And then we have a truncated normal, standard normal for sigma and for all the other variance components. The only new thing here is the prior on the rows. So the prior on the rows actually depends on a fact about variance covariance matrices, which is that you can decompose a variance covariance matrix into the standard deviations and something called a correlation matrix. And so what we will do is we will define a prior on the correlation matrix, right? So the fact that we will rely on is the following. Any variance covariance matrix, so let's consider 2 by 2 variance covariance matrix, like I'll call it sigma, let's call it sigma u1 squared here and sigma u2 squared. So this was our variance covariance matrix for subject, sorry. So I've got rho u and sigma u1, sigma u2, and then here also I have rho u, sigma u1, sigma u2, right? So the interesting fact is that I can break this thing up into 3 parts. So I'm going to break up this matrix into 3 parts. So one part will be the sigma u1 standard deviations, not the variances, written in a diagonal matrix. What I'll have here, oh, you guys can't see this, sorry. What I'll have, this is the diagonal matrix. This is a diagonal matrix. A diagonal matrix always has zero on the off diagonals. Okay, so this diagonal matrix contains the standard deviations, not the variances, standard deviations. The correlation matrix here will contain the correlation between the 2 random variables, and on the diagonals it will have the correlation of each random variable, that is u1 and u2, with itself, which is always of course going to be 1. So this is called the correlation matrix, right? And the last thing I'm going to do, can you see this? The last thing I'm going to do is I'm going to add another diagonal matrix here. I'm getting a heavy lag now. What's happening? This is really irritating. New note. I want to create a new note, so let's do that. How do we get rid of this keyboard here? Yeah, okay. So what I want to do is, so I'm going to rewrite this, sorry. So I've got sigma u1, sigma u2, okay. And then I've got zeros here. Then I've got a correlation matrix, 1s on the diagonals, correlations rho u on the off diagonals, and the last thing I have is another diagonal matrix, sigma u1, sigma u2, right, like this. So what's cool here, I'm going to demonstrate this, that if I do this matrix multiplication, I'm going to get back the variance covariance matrix. This is a fact. Okay, so let's do that. I'll just show that to you. So if you remember, the way that matrix multiplication works is that if I have, so reminder, right? So if I have something like x1, x2, x3, x4 multiplied, this is a 2 by 2 matrix. If I want to multiply it with another matrix which is like y1, y2, y3, y4, how do I do matrix multiplication? Do you remember? Okay, so the way it works is I'm going to take x1 multiply with y1, right, and plus x2 multiplied with y3. This gives me the result of this matrix multiplication. Then I will do x3 y1 plus x4 y3, right? That leads me to this part, and then I will do x1 y2, sorry, that's supposed to be a 1. Can I erase this? Let me try again. x1 y2 plus what is it, x2 y4 gives me the top right, and then the bottom right gives me is obtained by x3 y2 plus x4 y4, right? So this is how matrix multiplication works. You take this row and do a pairwise summation of the products with this one, and you do that with all the rows and columns. Okay, so that's how it works. So I'm going to do this now, right? So if I multiply sigma u1 time and 0, the first row here, sigma u1 0 with the first column of the correlation matrix, I'm going to end up with sigma u1, right? Because 0 multiplied with row u will be 0, so I'm going to get sigma u1, right? The second column, the top right matrix, will be sigma u1 0 multiplied with row u1, that gives me row sigma 1, right? And then 0 u2 multiplied with 1 row u will give me row sigma u2, and the last thing would be 0 sigma u2 multiplied with row 1, which gives me sigma u2, and you see where this is going now, right? Then I'm going to multiply this with the next diagonal matrix that's left, which is sigma u1 0 0 sigma u2, and what I get, lo and behold, right, you can see where this is going, will be sigma u1 squared, right? And then I'll get 0 blah 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 row sigma u1 sigma u2, and then here also I'll get row, sorry, this is row u, I meant to write row u every time, right? So what I get is row u sigma u1 sigma u2, and then sigma u2 squared. So you can check this yourself, right? So basically what happened was we decomposed the variance covariance matrix into the correlation matrix and the diagonal matrices, and we know that by multiplying these guys out, we can get back the variance covariance matrix. So what we do instead is that, or even in other Bayesian programming languages, is that you would define a prior on the correlation matrix, right? So I define a prior, which is the LKJ prior, right? LKJ correlation matrix prior with parameter 2. What this parameter is saying is that you are downweighting the -1 and +1 values. This is very valuable. This is a regularization step, right? And it's ensuring that the posterior will never have the properties that the posterior for the correlation will not have the property that you would get a +1 or -1 like you would with Elmer, right? That's never gonna happen because of this regularizing prior. And as I showed you in the lecture, you could play with this parameter and see what happens to the posterior. Okay, so try that out. You'd be a little adventurous, right? Put in a 10 there, or put in a half there or something and see what happens, or a 1. Okay, anyway, so that's the point now. And actually, technically there's more happening here that I won't discuss in this course. Actually, we work with the square root of the correlation matrix, and that square root is called a Cholesky factorization, or Cholesky decomposition, right? So what one does is that you take a correlation matrix, right? Call it rho. This is the correlation matrix. You basically compute the square root of the matrix, right? It's written L historically, and then you define a prior on the correlation, on the square root of the correlation matrix, and that LKJ prior, the LKJ prior is actually defined on that. So later in the course you will see this kind of stuff, but I mean, for now it's good enough, right? That we just think about the correlation matrix and assume that we're defining a prior on the correlation matrix. So the details you can unpack later. Okay, so basically I've discussed all this now, and so what we now have is this I've just discussed. And so basically the LKJ prior can be varied a lot. You can have a beta, something like uniform prior on the correlation parameters. Of course, you never want that, really. I don't ever want to do that, but you could if you wanted to. Okay. All right, so that's the story with the prior. The specification is easy now, right? You set up the intercept and the slope priors, the standard deviations, and the sigma are truncated normals. BRMS knows to truncate this, so you never actually say this explicitly, but as soon as you say standard deviation or sigma, that ensures that you have a truncated normal, right? So later on in the advanced part of this course, which Bruno teaches, when you start writing stand code, you're going to have to deal with this problem, you know, of defining a truncated prior. And then here's my LKJ2 prior that regularizes the correlation, you know, values for the intercept for the subjects and for the items, right? So the model basically looks very simple: log normal likelihood, intercepts and slopes, blah blah blah, and we are done, right? So that's the whole setup now. And then you will get all your posteriors for all the parameters, and you could in principle also look at the individual level differences. I think I've discussed all this now. You can see that some subjects are really slow, some subjects are fast, you know. So this is the bi-subject slope adjustments that you're looking at, the relative clause effect. Okay, so I've extracted the relative clause difference for different subjects, and you notice that many of the subjects are very slow here, are showing very large effects, and some are showing, you know, negative effects even they're finding subject relatives harder than object relatives. These wide credible intervals actually are telling you that you have very little data from each subject, which is understandable. We've got only 16 data points from each subject. So I mean, there's not much one can say here except that subjects vary quite dramatically. But I want you to notice that actually this subject 37 or something, or 39, this last subject is actually one of the two subjects. These two subjects are actually driving the overall effect. And if I removed these two subjects from the picture, I would not see an overall difference between object and subject relatives, which is quite surprising actually. Okay, so I think I discussed all the other stuff that comes in the rest of this lecture in the from the, you know, the second part of the lecture. So I won't repeat all this now, right? You can now look at the second lecture, which is already recorded, and that would be the end of this presentation here.